Hello, everyone. We're back in Chapter 1, Part 2 for the operating systems concepts. We're going to continue with the I/O structure. Well, last time we have talked about the interrupts and how they work and so on. I'm going to start with talking about the different models for handling the I/O. So let's say here you have the user program. Okay, and we have here the I/O. All right, so here is the I/O. As soon as the request happens, here is the request. One model is for the program here is working as soon as the request happens. One model is for the program to stop, and it keeps waiting for the request to finish. As soon as it finishes, then or completes, the user program takes the control again and starts working again. So this time interval, the user program is idle. Idle is the opposite of busy. Okay. So one of the models, the program will wait until the I/O is done, so it can use the data retrieved by the I/O and start, processing them and completes and so on. The other model is that as soon as the I/O happens, okay, the request, it starts retrieving the data and so on until the complete. But the program doesn't really stop. Okay, the program continues execution, and then in certain point of time, it will be utilizing the data when the data is being retrieved and the I/O completes. Okay, so those are the two different models. Here, the first one, after I/O starts, control returns to user program only upon completion. So the control will not return back to the user program until the I/O completes. What does it mean? The user program will not run. The program counter will remain where it is until the I/O completes. Okay. The other model, the control returns to user program without waiting for I/O complete. What does it mean? During the I/O is happening, the program counter proceeds and executes and so on. Okay, so there is no waiting here, which is kind of concurrent execution. So while the data is being retrieved by the I/O, the program executes. Okay. Which model is better? Which model is more common, and so on? We're going to be talking about it in later chapters. All right. So after I/O starts, control returns to user program only upon I/O completion. So that's the first model. Look what happens. Wait instruction idles the CPU until the next interrupt. The next interrupt would be the completion, right? Wait loop. Okay, so it keeps waiting. And at most one I/O request is outstanding at a time, of course, because it's sequential. No simultaneous I/O process. Why? Because everything will freeze until the I/O completes. What is the problem with this? It's literally sequential execution. Do you see? It's sequential. Okay, what is the problem with this? The problem is the utilization of the CPU. The utilization of the CPU. Imagine you have a company and you hire an accountant as an example. And every time, this accountant has to wait until documents get back for that accountant to proceed with processing and so on. What does it mean? It means that this accountant will not be working full time. If you have, let's say, 8 hours a day, this accountant probably will work half an hour here, half an hour there, half an hour there, and the rest waiting, right? So the problem with this one is the performance, right? The performance. The other model, no, the accountant will always keep working. You tell me, but the documents are not there. Yeah, the accountant will be working in different documents that is already there. Okay, so the utilization of your employee here goes up very high. Okay, so those are the two different. So it's always this way. Sequential behavior is not always favored, unless in certain situations, like in chapter 6, when you try to control what we call some critical sections and so on, we do convert the execution to be sequential. Rather than that, concurrent execution is the one that we are seeking to bring the utilization of the CPU up. The second one, after I/O starts, control returns to user program without waiting for I/O completion. How does this happen? Okay, look. We have a system call that requests the OS, to allow the user to wait for I/O completion, and then the device status table contains entry for I/O, each I/O device. What's happening here, for this one is as follows. The user, you have a user mode and operating system mode, okay? The program keeps running, the user program keeps running while the I/O is being performed. So you have here concurrent execution. It could be parallel, and I'll talk about the difference between concurrent and parallel executions later. Now, how does this whole environment start from the beginning, and how does the computer know about operating system? It's hardware, and then you install something on it, you call it operating systems, and the magic happens, and all of a sudden the software gets control on the hardware. How does this happen? Well, again, there's no magic at all here. What happens is when you turn the computer on, okay, you have something called bootstrap. We're going to be talking about it like in a few minutes. Here is the bootstrap. Where is it stored? It's stored in non-volatile memory, RAM. Okay, or EROM, of course. EROM is a special kind of RAM, EPROM. I'll talk about it. Okay, what is RAM? It's read only memory. What is RAM? Random access memory. So what is the difference here? The RAM is volatile. Okay, so when you turn the computer off, everything is gone from the RAM. When you turn it back on, it's initialized with what we call garbage. Okay, it's actually a scientific term, which means random bits being populated by either ones or zeros. Okay. The ROM is read-only memory. So here is the ROM. You put a bootstrap on it, so it's saved once and it's always there. Here is the program, the bootstrap program. The bootstrap program, what it does is it initializes your computer. So it checks all the hardware in there, if there is any problems or not, and so on and so forth, and then load the operating system. So you tell me, how is this possible? I mean, how does it know which operating system to load and so on? It doesn't really. See, it's very simple. On the hard disk, imagine that this is the storage. Of course, the older ones. Here is the hard disk. Looks like that. It's like the pizza. Here it is. And those are called sectors, right? And the sectors are named from 0. It goes all the way until n-1, where the number of sectors is n. Sector 0 has the script to load the operating system, to initialize the operating system, and so on and so forth. So what does the bootstrap do? All it does is read this one into memory, RAM. So it loads this one, it puts it into the RAM, and get the program counter to execute it. That's it. And according to the code written, the operating system will be loaded. So if it's a Linux operating system, the script that is being here is, how you can load a Linux, which is in sector 0. If it's a Microsoft DOS, the one related to the Microsoft Windows, whatever that is, depending on the operating system, the script will be different, but it will all be loaded here. All the bootstrap does is load it in memory and then get the PC, the program counter, and starts executing the code. Okay, that's why in the late 80s, early 90s, we had a virus that used to write itself on sector 0. So even though you installed, let's say, Windows or whatever, when you start turning your computer on, it tells you there's no operating system installed, and you're sure you just installed the Windows or whatever operating system you installed. Why is this? Because even though operating system is written in the hard disk, the scripts that loads it got destroyed by the virus, because the virus writes itself into the sector. So when the bootstrap tries to read this one, it reads garbage. Okay, so the code that is being written is not recognized. And that's why the computer tells you, oh, sorry, there is no operating system installed. So back to this bootstrap program. Here it is. It's loaded at power up when you turn your computer on, okay, or reboot, of course. Typically stored in ROM or EPROM. I didn't say the difference between ROM and EPROM. I'll talk about it. And this one, of course, is, the firmware. What does it do? The code that is being written here, it initializes all aspects of the system. It makes sure that all the hardware is correct, and so on and so forth. And it loads operating system kernel. How does it know it? The kernel of the Windows, again, is different from the DOS, is different from the Linux, is different from the Unix, is different from the Mac. Okay, how does it know it? Well, because the details of how to load the operating system, as I mentioned, is stored in sector 0 on the hard disk, and that's what the bootstrap do, is read whatever written in sector 0, load it into memory, get the PC, the program counter, and then it starts executing the code in there. So what is EPROM? This is erasable, programmable, read-only memory. So you can literally have a ROM, but then you decide later to erase the contents in it and then reprogram it again. Okay, once you reprogram it, it's permanent. Okay, until you decide to re-erase it again, and so on and so forth. All right, now, storage structure. You have the main memory. This is only large storage media that the CPU can access directly. What is it? When you go and buy a computer, you would say, the memory here is now 8 gigabytes, right? 16, it's 64, and so on, right? So this is the main memory that you go. And by the way, it's always 2 to the power something, okay? So you will not find a main memory with the size 50,000 as an example, because 50,000, you cannot put it in the term of 2 to the power n, and n remains an integer, right? N will be a floating point. So it has to be 2 to the power n, and n is an integer. So 64, as an example, is valid. 128 is valid, and so on. It's volatile. Okay, so the main memory is random access, as I mentioned, RAM, random access memory. It's volatile. So what does it mean, volatile? When you turn the computer off, everything's gone. Usually it's in the form of DRAM. This is really hardware aspect. We're not gonna go there. You have secondary storage, which is usually non-volatile, like your hard disk. If you have a tape, no one has tapes now, and so on. So you have here the hard disk. The hard disk could be HDD, okay, hard disk drive. We have a different type that we're going to be talking about later. All right, so this is basically, a disk surface that is logically divided into tracks, okay, which are subdivided into sectors. So here is the hard disk, as I have do it before. So those are the tracks, okay, and then you have divided into sectors. So those are the circles are the tracks, and the lines are the sectors. You also have non-volatile memory devices faster than hard disks, okay. We'll talk about